I want to try a little experiment with you. So just for a second, I want you to close your eyes.
Okay.
I'm going to say a word and just be totally honest about the very first image that pops into your head. Don't filter it. Ready?
Ready.
The word is wetland.
I am willing to bet you're not picturing a white sandy beach.
Not even close, no. If you're like me, you probably pictured mud.
Mm-hmm.
Just lots of sticky brown mud. Maybe a swarm of mosquitoes buzzing around your ears. A weird smell.
Yeah, a useless swamp.
Exactly. A soggy patch of land where you lose a boot and, I don't know, catch malaria.
And that's the standard reaction. It's the swamp thing rising from the deep. We've historically viewed these places as wastelands.
Right. We even have idioms for it. Drain the swamp.
Of course.
It literally means to get rid of a mess.
Yeah.
The swamp's the problem.
And that perception is exactly what we need to sort of dismantle today. Because if you look at the research we've pulled together, that whole wasteland narrative is just dead wrong. It's actually dangerous.
So that's the mission for this deep dive. We're going to try to convince you that these muddy patches are, in fact, some of the most high-performance biological machines on the planet.
And we're focusing specifically on Kenya.
On Kenya, yeah. On these working landscapes, the massive Yala Swamp, the Tana Delta, and even those little overlooked green patches right in Nairobi.
And we aren't just talking about, saving birds, though the birds are obviously important.
Right.
We're talking about biological infrastructure. We're talking about kidneys, sponges, and vaults.
Vaults, like a bank vault.
Exactly like a bank vault. In fact, there's a statistic in the source material that it absolutely floored me. It's about carbon.
Oh, I think I know the one you mean.
Yeah.
It's the one that compares them to forests.
That's the one. So we always hear about the Amazon rainforest, right? The lungs of the earth.
Sure.
But peatlands, which are a type of wetland, they cover only about 3% of the Earth's land surface, just a tiny fraction.
Okay.
Yet they store more carbon than all the world's forests combined.
Wait, hold on. Just say that again. 3% of the land stores more carbon than every forest on Earth. The Amazon, the Congo, all of them.
All of them combined. We're talking roughly 600 billion tons of carbon.
That's just wild. I mean, trees are huge. Moss and reeds are. They're tiny. How is that physically possible?
It's all about the mud, actually, which we'll get to, but that gives you a sense of the stakes here.
Yeah, it does.
But before we get into the chemistry, let's just define our terms. We keep saying wetland. It feels like a catch-all word.
It is a catch-all. I mean, in the research, we saw marshes, swamps, bogs, fens, mangroves. I couldn't tell you the difference between half of them. They just mean wet.
They are all wet, yes, but the distinction tells you what the ecosystem is doing. The simplest definition is really just any place where land and water meet.
The transition zone.
The transition zone, exactly. Permanently or seasonally. So let's map that onto Kenya. If you're out in the Yala Swamp near Lake Victoria, what are you looking at?
Okay.
Yala is a classic marsh, and a marsh is dominated by herbaceous plants, soft stems. So grass.
Grasses, reeds, rushes. In Yala specifically, these massive beds of papyrus. If you're in a boat surrounded by a wall of green stalks swaying, you're in a marsh.
Okay, so marsh equals grass. Got it. What about the coast?
Down on the coast, near the Tana Delta or Lamu, you find swamps. And in ecology, a swamp is dominated by woody vegetation, trees and shrubs.
Mangroves.
The mangroves, exactly. If you're navigating through those gnarly tree roots going straight into salt water, you are in a swamp.
Okay, that's easy enough. Marsh is grass, swamp is trees. But then we get into the really nerdy stuff, the peatlands.
Bogs and fens.
This is where I got a bit lost in the notes.
Okay, so think of peatlands as a category defined by their soil. These are places where dead plants build up over thousands of years to form peat.
Right.
Now, the difference between a bog and a fen is fascinating. It's all about where the water comes from.
Okay, break it down for me.
A bog is fed almost entirely by rainwater. And rain is, it's pretty clean, but it's also slightly acidic and very low in minerals.
So a bog is an acidic environment. Very acidic. It's like a giant cup of tea that's been steeping for way too long. The water is dark and tough for most plants to survive in.
And the ground feels weird, right?
Mm-hmm.
The notes mentioned quaking.
Yes. The Ondiri Swamp near Nairobi is a great example. It's a quaking bog. It's basically a thick mat of vegetation floating on water.
So you could jump on it.
You can jump on it, and the ground ripples like a waterbed for 50 feet around you.
That sounds like a great way to disappear forever.
It is a little unnerving. But now contrast that with a fen. Fens are fed by groundwater, so water that's flowed through rocks and soil.
Oh, so it's picking up minerals along the way.
Exactly. Calcium, magnesium. So fens are less acidic, they're more alkaline, and because they have more nutrients, they can support a much wider variety of plants.
But both of the vaults we mentioned, they're both building that peat layer.
That's the key. They are building the vault.
We are definitely coming back to the peat because that's the carbon story. But I want to talk about this kidney metaphor. It's a great image, but when I look at a wetland in Nairobi, it doesn't look like a sterile organ. It looks like a trash collector.
Well, that's because it's working. You don't judge a garbage truck by how clean it smells.
Fair point.
You judge it by how much trash it's taking away.
So how does it work? How does a patch of papyrus act like a kidney? Is it really just a filter?
It's more like a three-stage process. First, you have the physical part.
Okay.
Imagine a heavy rainstorm in Nairobi. Water rushes off the roads carrying silt, oil, plastic bags. It's moving fast.
A flash flood of dirty water.
Right. When that fast water hits the dense vegetation of a wetland, it slams on the brakes.
Friction.
Friction takes over. And when water slows down, gravity wins. The heavy sediment, the silt, it just drops to the bottom.
Okay, so it traps the solids. That makes sense.
Then you get stage 2, which is chemical. This is where the plants really get involved. Runoff is often full of nitrates and phosphates, basically fertilizer.
Which is really bad for rivers, right? Creates algae blooms.
Terrible. If that nitrogen goes straight into Lake Victoria, you get those massive blooms. The water turns neon green, oxygen gets sucked out, and the fish die.
So the wetland stops that.
The plants in the wetland, the reeds, the papyrus, they look at that sewage and they basically say, yum.
They eat it.
They literally eat the pollution to grow. They are cleaning the water that would otherwise kill the lake.
That's incredible. But what about the really nasty stuff? The toxins, the stuff plants can't eat?
That's stage 3, the biological treatment. It happens in the mud itself.
In the mud.
In that oxygen-poor, swampy soil, you have billions of specialized bacteria and microbes, and these little guys can break down complex organic pollutants, pesticides, even heavy metals.
I saw a stat on that which seemed almost too good to be true. That wetlands can remove up to 60% of metals and 90% of nitrogen.
It's true. 90%. That is industrial-grade efficiency.
And they do it for free.
For free. You know, if we wanted to build a treatment plant to do what the Yala swamp does, it would cost billions to build and millions a year to run.
The swamp just sits there and does it.
It just sits there.
So when we see a dirty-looking wetland in Nairobi, we shouldn't be disgusted. We should be grateful. It's taking a bullet for the whole river system.
Precisely. It's cleaning the water before it gets downstream.
Okay, so that's the kidney. Now let's talk about the sponge. This feels really relevant because every time it rains heavily in Nairobi now, the roads just turn into rivers.
And that is a direct result of ignoring the sponge effect.
How does it actually work physically?
Think about a dry kitchen sponge. If you pour a bucket of water on, say, a concrete block, what happens?
It splashes everywhere, runs off immediately.
Right. That's a city without wetlands. But if you pour that same bucket onto a dry sponge,
It just holds it, it soaks it up, gets heavy.
it absorbs the shock. In the Tana Delta, when the river swells during the rainy season, the surrounding wetlands absorb that huge volume of water. They spread it out.
They lower the peak flood.
Exactly. Instead of a violent wall of water rushing downstream, you get a much more gradual rise. It buys time, it buys safety.
Okay. But what happens when the rain stops?
That's the other half of the magic trick. During the dry season, the sponge slowly squeezes out.
Right.
The wetland gradually releases that stored water back into the river, into the groundwater. It keeps the Tana River flowing when it might otherwise just dry up.
So it's flood control during the rain, and it's a water reservoir during a drought.
It buffers the extremes.
Yeah.
And in an era of climate change where weather is getting more extreme, that buffer is everything.
And yet, in cities like Nairobi, we're doing the exact opposite. We see a wet patch and think, great place for a new bypass.
Or a shopping mall. We pave over the sponge, and then we act shocked when the expressway floods 3 months later.
We remove the very thing that was managing the water for us.
It's like taking the shock absorbers off your car and then complaining about the bumpy road. We're dismantling our own life support system.
Okay, so we've got kidneys and sponges. But let's go back to the big one, the carbon vault. You said they store more carbon than forests. I really need to understand the mechanism. Why doesn't all that plant matter just rot away like it does in a forest?
It comes down to one word: anaerobic.
No oxygen.
Right. Picture a tree falling in a forest. It's on the ground. It's exposed to the air. Fungi and bacteria that love oxygen attack it. They eat the wood, break it down.
And the carbon goes back into the air as CO2.
Exactly. It's a fast cycle. But in a wetland, that dead plant material falls into the water. It sinks into the mud, and the water blocks the oxygen.
So the normal bacteria just can't get to it.
The oxygen-loving ones can't. So the whole decomposition process slows to a crawl. The plant matter doesn't really rot. It pickles.
It pickles.
Effectively, yeah. It compresses into these layers of peat, and that carbon stays trapped in the plant structure, buried for thousands of years. We found bog bodies in Europe, right? Humans from 2,000 years ago, perfectly preserved, skin, hair, everything.
Because the rot couldn't get to them.
Exactly. So a peatland is like a biological time capsule. It locks carbon away.
Okay, but this sounds incredibly fragile. Because if the water is what keeps the oxygen out, what happens if we drain the water?
And that is the double-edged sword. It's a terrifying concept.
So walk me through it. We decide to drain part of the Yala swamp to plant maize. Water level drops.
And air hits the soil. For the first time in centuries, suddenly all those dormant microbes wake up. And they are hungry. They start feasting on that ancient peat.
And when they eat it,
they release the carbon rapidly. A drained peatland stops being a vault and becomes a chimney, spewing CO2 into the atmosphere.
so it's literally a carbon bomb.
It is. We go
Yeah.
from actively cooling the planet to heating it up just by digging a few trenches.
I have to play devil's advocate for a second, though. I remember reading that wetlands also release methane.
They do.
And isn't methane a much worse greenhouse gas than CO2? So,
Yeah.
aren't they actually bad for the climate?
That is a very sharp question, and it's a common point of confusion. And yes, healthy wetlands do emit some methane. It's a byproduct of those anaerobic bacteria, and methane is potent.
So we're just trading one bad gas for another.
In the very short term, it can look like a trade-off. But the science is clear that the sheer volume of carbon being locked away in the soil far, far outweighs the warming effect of the methane emissions.
So the overall math works out in our favor.
A healthy wetland is a net cooler of the planet. But, and this is the critical part, a drained wetland releases massive amounts of CO2 and stops storing any new carbon. So the only winning move is to keep them wet.
Keep them wet.
Yeah.
That seems to be the mantra. But looking at the reality on the ground, we just aren't doing that.
We're not. The statistics are just grim. Since 1970, the world has lost over a third of its wetlands.
Yes, in our lifetime.
And if you go back a few centuries, it's nearly 90%.
What's driving this in a place like Kenya? Is it just people needing more land?
It's a mix. Agriculture is the big one. In the Yala swamp, there is this constant tension. You have investors who look at that marsh and they just see potential.
Potential for farmland?
Thousands of acres where they could grow sugarcane or maize. And food security is a real issue. You can't dismiss that.
Of course not.
But the irony is, by draining the swamp to grow food, you might destroy the very water cycle you need to grow that food in the long run. It is the definition of short-term gain for long-term collapse.
And then you've got things like invasive species, right? The water hyacinth.
The green carpet?
Mhm.
Parts of Lake Victoria look like a golf course. That weed just chokes the life out of the water. It blocks sunlight, kills native plants, and stops that kidney from working at all.
And in Nairobi, it's just pure urbanization.
It is. We see a wetland as a blank space on the map, a space that's just waiting to be filled with concrete.
It really all comes back to that first image we had, the mud. We see mud as a problem to be solved.
When we should see it as a solution.
So if we're going to wrap this all up, we've toured the machinery, they clean our water, they stop our homes from flooding, they keep the planet from overheating.
So what's the big takeaway?
I think for me, the shift is to stop seeing it as nature versus development. In Kenya, protecting nature is the development.
I agree completely. You cannot have a water-secure Mombasa without a healthy Tana Delta. You can't have a livable Nairobi without its urban wetlands acting as sponges.
They really are working landscapes.
They're working harder than we are most of the time.
There was a point in the research about indigenous knowledge that I think just summarizes this perfectly.
Yes, traditional communities around the Delta, they didn't try to conquer the swamp. They didn't build giant levees to keep the water out.
They adapted.
They moved with the flood and the recede. They saw the wetland as a partner, not an enemy to be defeated.
Exactly.
Right?
And here's the thought I want to leave everyone with today. In our modern rush, we always look at a piece of land and we ask, what can I build on this?
How can I change it to make money? Right. How many condos? How many crops?
But the question we should be asking, the one that might just save us, is what is this wetland building for us simply by being left alone?
It's building resilience. It's building a future where we don't have to spend billions on water purification plants because the mud is doing it for free.
The most valuable thing the wetland does is just exist. So next time you see a patch of soggy ground or you get a little mud on your boots, try not to think wasteland.
Think kidney, think sponge, think vault.
And give a little nod of respect to the mud.
Respect the mud. I like that.
Thanks for taking this deep dive with us.
It's been a pleasure. See you on the next one.